afternoon, good evening, good morning to everyone. After 2 weeks of break, we are here with a new focus meeting by Fabio Maltoni and Andrea Wulzer on the precision potential of the LHC and also the high-luminosity option. So I leave the microphone to David, who will introduce the speakers. Thank you for being here.
Yes, thank you, Stefania, and to everybody. Today we have Fabio will give the first part, and then Andrea Wulzer will discuss the second aspects. So before introducing Fabio, maybe just technical things. So this is a focus meeting, so there will be a discussion session at the end of the two talks where we have a panel of 4 experts. We have Sally Dawson, Christophe Grosjean, Michelangelo Mangano, and Adam Falkowski. They will start the discussion, and then everybody is welcome and invited to participate to the discussion. So after each talk, and in the middle of the talk, we would prefer to accept only very urgent questions. Okay. So let me introduce quickly the first speaker. Fabio Maltoni got his PhD in the University of Pisa. Then he had several postdocs in Turin and also at CERN. From 2006, he was staff at the University of Louvain. Okay, and since a few years, he's a professor in Bologna, University of Bologna. Fabio Maltoni is an expert one of the leading experts in QCD, collider physics, with a special focus on the applications to new physics searches and high energy collisions and precision test of the standard model. And he's famous for being one of the authors of the MatGraph tool that all the community uses to simulate collision events at colliders. Okay, so I leave the stage to Fabio and the talk.
Thanks, David. Thanks, Stefania, and everybody, the organizers. It's a real pleasure to be here today with you all. I mean, it's also an exciting time. We are about to restart with run 3 and LHC, as we'll show in a moment, and we have a very long way to go, as I will try to argue, and a lot of momentum right now towards our goals, so that will be a bit of discussion on the team, like the spirit of this seminar that we will be all attending today. So Andrea and I have been asked to talk about suggested to talk about the precision potential of our highest energy accelerator and LHC. So let's have a look. Let's start and look what we have done and what is ahead of us, right? So this is a schedule of the machine. We are where the today line is, time equals 0. And we are about, as I was about to say, to start a new run, the third run, where we will reach about 400 inverse femtomers of luminosity. Now, you see from this plot, right, that somewhat it looks like we are in the middle of it, no? Because if you just look by eye, it seems that we are in the middle of our path. But actually, if you look a bit more carefully, you see that around here, there is a log scale coming in, which I expand into a linear one, and see that actually it's still a long way to go. Right? We are just 10 years in, 10 years in of our physics program. Relatively to the span of the machine, we are at 1/3 of our adventure timeline. But in terms of data that we are going to gather, we are just 1/20th, more or less, right? So we have a very tiny bit of the data that we will get from the machine in the next somewhat time scale of 20 years. So we structure this discussion today with having in mind the new generation, the young generation of the students who we have just learned and we have just listened to a few minutes ago in this very nice Cortona Young forum, where we listened to fantastic presentation of very energetic young generation guys. And so what we really would like to do today is to try to convey the idea of the challenges that are ahead of us, right? So this is a bit the spirit. So we are not going, at least I will not go very much into detail things. I will try to flesh out where we think we need your help. We need the help of the new generation of people, of the bright students, of the bright physicists that are growing up as theorists, as phenomenologists right now. So making a comparison, right, an analogy with the trip of Magellano few 5 centuries ago, you know, you remember that he went through the world in about 3 years. So if you make the proportion, we have just started, we are in the Canary Island right now, from what concerns the luminosity, right, the data collected, and we have just reached the stretch of the Todos los Santos, where is the Capo di Buona Speranza in Italy, where, no, sorry, it's the other one, where is where bad water is, right, is where really challenging waters are, and we are about to cross them. So it's a long way. I like the fact that, of course, Magellano then went back to the same place, right? But along the way, he learned a lot, right? So we don't know yet if we are going to go back to the same place or not. We don't know if we're making a discovery which will change the way we see the world. However, whatever that is, our trip, as usual, right, in all trips that we take, matters more than the destination that we will get to. So what do we stand? We had a fantastic, 2 weeks ago, we had a fantastic tea seminar with many of the leading figures in the world right now that are thinking about what is beyond the standard model. And I like this plot of the spherical cow that Riccardo Latazzi mentioned 2 weeks ago, about the fact that our standard model is a bit like a spherical cow. It's a simplified, accidentally symmetry dominated model, which we now start to learn a bit more in detail. Only 10 years ago, we didn't know anything about what is in red here. And now, since 2012, we are start learning about the Yukawa sector, the mechanism of generation and the dynamics and the coupling of the scalar field to the vector bosons, and I'm not comfortable to say that we are learning anything yet about the potential of the Higgs. So let's say that we are working towards it. We are working towards trying to understand whether this potential is what the standard model predicts it is or not. So it's a fantastic construction. Somewhat, there are many things that come out of this model that we didn't put in, but certainly we have several aspects that we learn in school, right, which still somewhat surprises us. And the matter is organized in multiplets that somewhat get to an automatic and anomaly-free theory. It's renormalizable because it's four-dimensional, but this idea of normalizability, again, should not detour us from the fact that we think, after all, that what we are seeing now is a lower energy manifestation of some more complete or extended anyway theory. So in fact, it's so, the way that we see, we're used to see the standard model is such that a closed system that is actually even working. There is no indication, right? It's dimension 4 system, so we have no indication of the scale where it will break, right? As it is now, it looks like if you only look at this bit, we have no indication. And in fact, from the parameters of the theory, the numbers that we measure in experiments, we also see that somewhat it doesn't break down even where it could have broken down because of loop effects or quantum effects at some higher scale. But this doesn't happen. Even this could have happened. We could have been in the red region here. We could also be in the green one where there is no indication that the vacuum is unstable. Actually, we seem to believe that if the standard model is valid up to arbitrary scale, let's say, we seem to live in a meta-stable region. So if the standard model is correct to very high scale, actually, we don't even know. It doesn't have a very clear indication where it might break before the gravity scale or gravity scale where gravity becomes comparable with the other interactions. So what is the side, right? The experimental side of our theory adventure? Well, it is very well represented, I think, in this very nice plot that you see in all, basically, in all conferences dealing with high energy physics, sooner or later. Right? It shows the cross sections ordered by size. So the rarer processes are on the right and correspond to smaller cross section on this y-axis. And what we also see in color are the experimental measurement. And in gray behind them, not very visible in the background, there are also the theory prediction, which most of the time you don't even see because their uncertainty, the uncertainty in the theory is typically smaller than the uncertainty that we have in the theory, in the experimental measurements. So this is normally presented like a success, right, of what we have so far. The way that I feel it is, it's really a success from experimental point of view. It's a success for all the people that work in making prediction as accurate as possible. But the way we should look at this plot is a stepping stone. Is the way through which we are now ready to actually go there and find something else. Is our, check, right? Is our sanity check that we are ready to take a jump, to take the leap into something that we don't know and we don't, maybe we don't understand that is coming, maybe is lurking behind this picture. So if I have to make an analogy with the building of the Eiffel Tower, we are here. So this plot is just the foundation of what is going to happen in the next 20 or so years. So what we have learned so far, there are many things. I'm not even trying to make a summary here. I'm taking just a few of the very well-known points, right? We are checking this linearity or quadratic relation between the coupling of the Higgs to the Fermi and the Yukawa, and also the coupling which is quadratic with the gauge bosons. And if I plot them in a clever way, the standard model tells me that I should find a line, right? A straight line, even in a double log plot. And you see in colors here our measurement. So these are two measurements actually in one plot. For each point there is a measurement in the x-axis, there is one in the y-axis, and then I put a dot where they cross, right? So two measurements per point. One is the mass of the particle, the other one is the interaction, the strength of the interaction. And as we could not even dream 8-9 years ago, actually this coupling, as far as we know, they magically align on the standard model prediction. So there are two things here that are worth mentioning. The first one is the fact that we actually are getting the first measurement of the Higgs coupling into the second generation, or let's say what we call the second generation conventionally in the standard model. There's nothing special about being first one or second or third, but the muon, we never seen any coupling to the second generation fermions, and now we have a compelling evidence already. It's not 5 sigma, but it's getting close closer and closer, and is aligned there. And remember, the muons, you know, these days are the hot guys, right? Are the particles which attract all our attention. So the fact that that point is on the standard model is by itself bearing a lot of meaning and should attract our attention. Not again, standard model is there, but very much into that point might be actually telling us something which we don't understand yet. On the other hand, on the right-hand side, you see some kind of summary from one of the two collaboration, the CMS on the left, Atlas on the right, where we somewhat compare with the prediction of the standard model, which are here aligned with one, the measurements of some kind of fiducial cross-sections into some final state. So these are production times branching ratio for some final states. The first one is GG to gamma gamma, and these are called mu in the slang of the experimentalist LHC. And you see, mass standard model predicts mu equal to 1, and you see that there is a fair agreement with the standard model, but with some channels that somewhat have still a large uncertainty. You see, the uncertainty can be as large as 100%. So some of them are known rather precisely. We are in around 10, 20, 30% uncertainty. Others, we know them with a little bit less precision. There is a very important missing ingredient in this plot, which some of you might have noticed. There is no Higgs particle. Why? Why there is no Higgs in this plot? We know the mass of the Higgs extremely well, actually. 2 significant digits, almost 125.09 GeV. So why we didn't plot it? Because we are not measuring yet, and that's what I was saying before. We are not accessing what is the coupling of the Higgs with itself. And notice something very important in the standard model. There is a striking prediction in the standard model which says that once you fix the mass of the Higgs, then the trilinear and the quadrilinear self-couplings are fixed. There's no freedom anymore. Both of them are tied to the coupling, to the mass, to the value of the mass. So if you want to break this, if you want to deform the spherical curve that we were talking about before, then you have to do it in a way that somewhat you have to modify both lambda 3 and if you want to test the theory even more, even lambda 4, right? So we will use this language in a moment, but this is somewhat important to remember from the following. In the standard model, the quadrilinear coupling of the standard model are always related to the trilinear and always to some other basic parameter. So there is this degeneracy in these strong constraints that you might want to deform if you want to really test the standard model. So what do we know? Well, we know that if, now that we know the mass of the Higgs, if things are standard model-like, well, we have a big problem because the so-called symmetry, matter-antimatter symmetry in the universe might not be dealt with the phase transition of the Electroweak phase transition, because as you see here, with the mass of the Higgs of the standard model, like with the potential of the standard model, we expect a transition of the second order. There is no boiling, there are no bubbles in the universe, and while if you change the potential, you see a transition of the second order, right? There is a potential here, barrier, and if you get through, if you get a bubble, right, then you can transit to another minimum that goes down. So if you want the asymmetry to be in the universe, you need the universe to be boiling at some point in its history. And this is not possible in the standard model because the Higgs is too light, kappa is too small, this kappa lambda, this lambda 3 is too small. And people studying on the lattice, non-perturbative computations shows that you need something like 1.5 the value of lambda in the standard model to get something that is close to a second order phase transition. So we need to increase the value of lambda. And the other point is that we need to know lambda rather well, lambda 3, I mean, to actually pin down what will be the mechanism. Will be just a normal transition, a two-step one, and so on. So we will need much more information. We need to pin down this coupling extremely well if we want to have a chance to understand what the mechanism might be. So where do we stand? It's also interesting to know where we stand, and that ties back to the comment I did in the beginning. Do we know anything about gamma lambda? What do you mean by anything? Well, we mean in the range of something that actually corresponds to some model. The answer, well, we can discuss about it, but roughly speaking, the answer is no, right? I mean, we have very loose bounds. You see from here, from -5 to 10, something like this. And you see it also from this plot in Atlas. These are a double plot. It's kappa lambda and also the coupling of the top, because the way we measure double Higgs also involves the Higgs coupling to the top. So we normally do a two-dimensional plane here. But bottom line, you see from this plot on the right, very clearly, the information we have on kappa T is way more precise on the information we have on kappa lambda, right? You see it from the scale. On kappa T, we are learning something. We are learning the Higgs coupling to the top closer, right, within 20% of the standard model prediction, and we exclude different physics model. With kappa lambda, we are not there yet. Right? We are still exploring to get to the point where we get information. So how do we get this information at LHC? Well, no free lunch at LHC. It's a hadron machine. We need to work hard to get the prediction that we need to compare with our theoretical understanding. There are three pillars which we base our predictive power in the standard model. There is a way that when we do computation at fixed order, we are systematically improving them. There is a summation point of view, which makes that, you know, in some phase, for some effects in some currents of phase space, there are higher order effects, which however are universal somewhat in each order, and we resum them. And then we have non-perturbative input we have to know to get the prediction. These are encoded in what we call partial distribution functions. So what is the, you know, the ballpark, you know, the game that we play, right? So a bit of naming, nomenclature here. So whenever you listen, you hear to next to leading order, well, that's the minimum, right? So that's the minimum accuracy that we need to do anything which makes sense. When you listen to next to leading order, well, this is really hard already to get prediction out of, and is where we get control of the uncertainties for the first time. Well, you have to be careful also if we're talking about QCD or Electroweak. NLO Electroweak is actually comparable to NNLO in QCD. And then you will hear actually that we actually now talk about NQ-LO. This is the frontier. We've broken this frontier since a couple of years. So it's very recent development. And this is where we start talking about this mantra, which is the 1% missing higher order uncertainties in this business of precision, which somewhat gives the idea that our final goal, our reasonable goal for prediction, for precise prediction in the LHC is around 1%. So where do we stand with precision computations? This is a slide taken from Gavin, who is a leading expert in the field. I will talk about his work again later when we have opportunity to do that. So it's a summary of what we gained by going from next to leading to next to leading. Actually, this slide was recent, but I even had to add a few instances here. So I hacked this plot down here because very recently, like months ago, we've broken another wall. We've broken the wall of doing computation at next to leading order with a multiplicity which is 2 to 3. This is even more complicated. There are pentagons in two loop pentagons and boxes and things which are extremely complicated to get. But the field is going fast, and this field of the computations is on a fast train and is achieving, as you see, the red lines, the red is the uncertainty of the next to next, and you see my high is reaching the place where we are around the 1%, right? It's a bit more, we are not there yet, but we are breaking walls in this direction very much. So there's been a fantastic result, as I was saying, the work of several years to get to a new result, which is n cube and all. We call it an n cube revolution. Why? As I said, because this brings uncertainty. This is the theory uncertainty parameterized by a normalization scale is one of these parameters that we use to identify the residual uncertainties from missing higher orders. And you see here the path even in history, right? Leading order, next to leading, next to next, next to next to next, with a reduction of uncertainty, with a picture, with a consistency picture that increases, right, as we get higher. You see that this line crosses with our next to next prediction, and it goes into the percent level. We also had now, very recently, the differential prediction at n cube below. So now this is the new black, if you want, the new standard, right, to beat in our field. Why is so important? Because we just added an n? No, because as I said, it breaks the wall of the 1%. The other thing it makes manifest, if you look at the budget, the uncertainty budget in this computation, it goes back now, it tells you that the ball goes back to the PDF, to our non-perturbative calculations and determinations for the input of these predictions. Because you see by eye, right, the red here and the blue here, then this input is where we have the largest of all the uncertainties, which we have to beat if you go, we want to go to this 1%. So same story for Draghian. Draghian is our standard kernel, is the hydrogen atom in collider physics. And for the first time, a few months ago, we got magically, from the non-expert point of view, right, out of the box, years of very hard work, and the prediction for n cube Draghian. Right? And again, you see from these plots, which I'm not describing, this time we have two observations to make. The theory prediction stabilizes, but it actually does not overlap necessarily with n and n o at small scale and the mass of the v, for example, of the w. So that's interesting, right? There was something somewhat that was not caught by the usual way we estimate residual uncertainties from higher orders. The other thing is that indeed we're reaching again the point where we can go to the percent level if we control uncertainties from the PDF. So for an information is a bit the same. The information community have improved the result consistently and let's say with the same pace as fixed learning computation. You see then in this plot, I'm not going to detail, so I'm not making justice of this fantastic work from this community. I just want to show here this plot where the points, believe it or not, are experimental points with their uncertainty. This is one of the most precise measurement out of the LHC, is the PT of the dielectron in Draghian. And even though you don't see them, a low PT, these black points have their uncertainties. And you see that here theory is slightly lagging behind experiment. We need to work hard to match the experimental accuracy and precision in this case. This is not the case for the Higgs, where theory is still doing better if the Higgs is not a model as it looks like it is so far. So what about resolution? What about how we see it? Well, there is an important aspect of resolution that we are all using on everyday life, and it's a key ingredient for the experimental comparison with theory. And this is by now established that this very nice picture by Sherpa, one of these Monte Carlo authors, picture shows an event, right? An event is a very complicated object to describe, and the accuracy with which we describe both the accuracy and the flexibility is currently dominated and led by our Monte Carlo tools, right? So it's a real pleasure to learn that Brian Weber and Fabio Maltoni have just been awarded by the APS High Energy Particle Physics Prize for this achievement, for the achievement of bringing theory to the experiment and vice versa, to establish this bridge and to making comparison meaningful and various levels of accuracy. In fact, we are now able to match these predictions with the computation which I was telling you before. However, we still have a bottleneck, which is amazing to have, because after all these fantastic tools are still formally a leading log accuracy. It's the leading order of the resolution procedure. And all the efforts so far to bring this resolution, which is exclusive, which is really generating events in all phase space, to this level, to the next level of precision, and been a successful so far. We are actually making fantastic progress right now as we speak. This is some visual impact of the work by the Keith Hamilton and collaborators in the UK, where you see in my eye that we have now ways, in the green one, to try to keep our accuracy on the shower at next to leading log. So it's a formidable challenge. There are both subleading terms in the amplitudes, in the color. It's a fantastic adventure to undertake. So what is the status here? The state of the art, again, something happened a couple of years ago. We didn't think this would happen so fast, but now we can at least match next to the Lord prediction with partial shower. It's true that partial shower accuracy is still leading log, but we have a recipe that works not only for final states which are neutral in color, but also for final states like TT bar, which are colored, obviously, and for which a completely new approach had to be developed. It's still an approach that somewhat takes all the bits and combine them, right? It's a very fulfilling plot to see for an expert in the field, because now this has been on the table for many years, and now we can see, right, the comparison with experiment and a theory in a fully exclusive simulation, not pen and paper, but real events against events. So let's go back in a moment. David, how are we doing with time? Do I have?
How much do you want? Not 10 minutes. I think it's okay, because we started a bit late.
Yeah, well, I'll need more, something like 10 minutes at least, 15.
Yeah. Okay. Yeah.
So PDF, I mentioned that before. PDFs are our input. So is our knowledge of the PDF right now in the same level as NQ-below prediction I was showing before? The answer is no, right? We don't have the evolution at the same level. We need a for loop here, evolution, to match it. And there is part of it shown here. You can see from here that indeed the part which we know is at the level of 1% uncertainty. You see how flat is this curve down here for mu around equal to 1. This is again a plot of how we are improving. The flatter is this curve, the better is our prediction. But you see it also from the right-hand side. This is an exercise that has been done among all these PDF groups to see what is the level, right, of precision that we might reach with the LSC data. And you see that by running an High-Lumi LSC, we might beat the 1% level. This is a ratio, right, with respect to a reference. and the uncertainty. So this is some region in X where we can beat it. But of course, if we could build a EP collider after the High-Lumi, we could go well below the 1% level. We don't know if this will be done, and we don't know, right? I mean, this will happen after the High-Lumi. So the question is, can we actually try to do something before 20 years from now? The answer, I think, might be in the lattice, is where non-perturbative computations are performed. And there is a fantastic progress there, a number of very recent results and a lot of activity, a lot of momentum, both for trying to measure alpha S directly on the lattice from hadronic quantities, right? In the same way, so what we extract alpha S from a measurement, we could extract alpha S from the lattice, and with the same idea, with this pseudo PDF idea, is to actually measure quantity correlations on the lattice, write a factorization theorem like here, which will have power corrections, and from there, calculating the coefficient function exactly as we do for cross-section and LHC, extract the F. So this is a recent work where both the the computation has been done on the lattice, and this extraction done by the same tools that we actually use in LHC to extract the PDF. And you see that things don't work out yet, right? I mean, these orange and green determination are off by their uncertainties. So there is still work to do here, but there is a huge potential in the lattice to actually fill this gap and getting to the point in 10 years from now where we actually might measure PDF or add to our fit the contributions, the measurements of the lattice. So the question I have now, for all of us, I've chosen 3 of them. I've chosen the basic one. So say, with 20 more statistics, what can we aim, right? And the other thing is, how can we get there? And how we can frame the result in a mostly, promising and effective way. And then Andrea will pick up from here. And so we'll actually, I think, really dig into the most interesting part, right? What we will learn, or how can we maximally exploit this information? What are the strategies that we can use to make full use of the full data sample from High-Lumi? So 20-fold data sample, right? How better our measurements will be. So people have looked at this, and there was a strategy update last year that was going on after several years of preparation. So the summary is that, as I told you before, I'm using the Higgs because the Higgs is the new person in town, right? So I'm using the Higgs to measure it. And you see from this plot, I'm now measuring the kappas, right? So it's a way of parameterizing the coupling of the Higgs to the standard model particle. And we know this at 10–20% accuracy right now. What can we aim for? Well, studies that have been conducted in this framework show, and you see from here, that the same parameters, some of them, they can go down in the range between 2 and 4% using the same kind of data that we have used for so far. So making nothing really much more clever or pushed, or using area of phase space which are drastically different from the bulk of the production mechanism that is on the left-hand plot. So again, we hit this number, this magic number of 1–2%. What about the Higgs coupling? Well, I showed you before, what can we aim? Well, here, the situation is more difficult. we might get to the 50%, right? 50% is without being more clever, right? By doing what we have been doing so far, 50% is the limit where we might be saying something on baryogenesis, right? Just in the boundary, right? So this is certainly something that we really need to work more on. Fortunately, future collider experiment and a much higher potential FCC HH can go down to even better than 10–20%. So what are the questions for the youngest, right? I think, you know, one would like, are we ready, right? Is everything under clear and under control? Is this a clear path ahead of us? We have just to work? Well, the answer is no. It's not clear at all, right? There are many challenges that we haven't figured out, and we are in the exploration phase, right? So I think the right set of questions for us today are we ready to start this adventure, right? And we have a plan or a strategy. We know how to attack this. We have ideas, but it's fully open, right? The way we will get to the end of this adventure, I think nobody knows yet how, right? So these three pillars I was mentioning about before, what are the goals that we need to achieve? So I will not worry, personally, I don't want to upset anybody, but I'm saying the fixed order train is, you know, flying right now. It's going full speed, is achieving results which will be available even in a few years from now. There is a lot to do, but there is a strong community there, a strong interest. We have just seen in the first 3-loop 2-to-2 computation by Lorenzo Tancredi collaborators, fantastic results, and somewhat they're going the right direction. And what about resolution? I already said, right? There is a lot to do there. There is even basic things to do about bringing the shower to NLL accuracy. Not clear right now that we will ever have 1% here. So there is a clear open challenge, a lot of work to do there. PDFs, I already mentioned, is the main source right now of uncertainties and will stay so for some time if we don't go into a breakthrough, right? So what about the rest? Are there other technical challenges? So I'm giving you an example, right? So this is a completely technical thing, and it's somewhat apparently very little to do with physics, okay? But it's actually amazingly important, right? So we will get so much data from the LHC that basically we will not be able to sit and wait as we have been doing in the last 10–15 years for the Moore law to catch up with the power, computing power, and this space that we needed, right? That's basically the strategy that we have been following so far. And you see from here, we just use the baseline, we'll go out of money. So being out from this black band will mean that we will not have the resources to buy storage and computers, right? To analyze the data, or to collect the data. Right? And part of it is actually in our prediction, surprisingly. Monte Carlos are an important point of this pie. So what do we have to do with that? Well, we do have to do a lot, actually. So remember 15 years ago, there was a paper by Matteo, Gregory, and Gavin about finding that the KT clustering was possible to rewrite it in such a way that from n³ complexity was basically linear. So at the beginning we said, well, okay, fine, we'll get an algorithm will just run faster, and that's it. Well, it was not it, right? I mean, this spurred an enormous activity, right? What was one of the key results in the LHC era, which made CDF D0 and Chemical completely different business, opened up a whole thing of studies about QCD, jets, boost topics, even now is still in the forefront with machine learning and so on. So it was an algorithmic improvement that opened, right, a new life for QCD in jets and all practical applications. So what will be the next KT algorithm, right? What will be? We don't know, but we are exploring. There are GPUs right there, right out there. They're not the GPUs of 2013. We tried 10 years ago to try to run our Monte Carlos on them. We failed, so to speak, in complexity. We are, you know, a bunch of new guys, right? New machines, new tools, new blood is trying now with, you see, fantastic improvements again in time going from CPU to GPU. The new ways of computing might lead the way. The other one is this burst of machine learning. Andrea will mention them again. I'm not going there again. It's just a flash. We might be able, we might get to the point where our Monte Carlo will be neural networks. And as such will be 10 times, 100 times, 1,000 times faster, opening a way to Monte Carlo simulation, which will be completely different. We are exploring, we don't even know right now if this can really work or not. And then we even try future things like quantum computers. There have been several papers now trying to do computing matrix element using you know, optimization of a quantum bit. Right? Instead of summing over Elisthes and using 2 bits for 2 Elisthes, we can use 1 quantum bit. That's coding. We can use quantum showers to keep the correlation in the shower, so we can go beyond our usual classical flow, right, of Monte Carlo generation classical way, and go to a quantum computation which will keep all the correlations. We don't know what will be the technology that we'll be using, but it's certainly fantastic to be able to have this possibility. So in the last 5 minutes, even less, because in any case...
Hey, Fabio, how long do you, how many slides do you have more?
I just want to introduce what Andrea will say, but Andrea will say, so let me conclude quickly.
Okay, okay.
And, you know, I just want to mention the way that we will try to interpret the results with the EFT, and to the idea that we will use this model and enlarge it, right? Enlarge it to include the higher order operation, and to see and to use the standard model as it is, but seen as an effective field theory. So Andrea will talk about this more in detail. I just want to explain how we do this, and that's it. I will stop it. So we measure an observable, an experiment, right? We predict it with our standard model tool, the 4-dimensional one. And then what we do, we measure, we quantify possible deviation in this n parameter space, where we can compute the coefficients perturbatively, and we can fit a series of coefficients which somewhat quantify the higher order contribution, the deformations that we come from physics, which lies beyond the Electroweak scale. So what is the power of this? I think this is important to understand as a basics, is that in the correlation, right? So you might have small deviation for each. So the red point is our measurement or our theory, let's say, and the black and the blue is the measurement. You might have a very small deviation right here, but the pattern of deviations together might lead you to think, to see the direct pattern, something that in imprint of a UV theory from top. So not by looking one observable at a time, right? By looking at all observable, all deviations at a time, you might see that these deviations are not random anymore, but they follow a pattern. And this pattern might be the image or the imprint of some UV theory at higher scale. Okay, so I ran way over time, but in any case, I think this is anyway a good time to stop. So I jump to the point of my conclusion and leave the discussion for later, and pass the work and the word to Andrea, to you back. Thank you.
Thank you, Fabio. So maybe since we went a bit long, if unless there are very urgent questions for Fabio now, we can move the discussion after both talks. So yeah, I don't see any raised hand, so I think we can move to the second talk. I leave the chair to Andrea.
Okay, so let me very quickly introduce the next speaker for this focus meeting. Andrea got his PhD from CISA, then was a postdoc at several institutions, including EPFL, ETH, Barcelona. Then he moved to Padova, where he's a professor, and he also currently holds a position in Lausanne and at CERN. His research is mostly focused on beyond the standard model. He gave a very relevant contribution to the field of composite Higgs, and more recently, he focused on precision test of the standard model, machine learning applied to particle physics and future colliders. And I think these are the pillars of his contribution to this focus meeting. So please, Andrea, you have 35 minutes.
Yes, I'll do my best. Thank you. Okay, so let me. Right. Good. Okay, so hoping that you can see the slides and the pointer as well. You can? And hear my voice at the same time? Very good. So now I will pick up the same subject, of course, as Fabio, from a slightly more beyond the standard model perspective, even if you will see that what we're going to say is actually not that different. The talk is going to be very concrete, so I'm going to focus on the things that we can usefully do with this with our perspective and with the potential for precision that comes from the LHC. Because from the general general ideological viewpoint, that's very little to say for searching for new physics, for probing better new physics of fundamental interaction. We have to work and we have to exploit all the opportunities that are offered to us. And as Fabio already said, there is 20 years of opportunities that is open at the LHC and its high-luminosity extension, which is not a fusion collider, it's a present collider. Okay, it's going to exist, and in this framework, as we have heard from Fabio, there is a new opportunity, new in the sense that 30 years ago, you would not have thought at the LHC as a precision machine. You would not have thought that the LHC could have systematically had the power to make such a great number of measurements to call for the design of what we call a concrete and extensive precision program. And this comes from a number of remarkable progresses that have been achieved already, because PDF are maybe our bottleneck, but PDF determination has improved a lot to a level that still already yet allows us to do many things. That is to say that we have to exploit the new opportunities that come from progresses that have been made in the area. So how do we think to this precision program? Sometimes we think to that, or we hear about that as a quote-unquote standard model precision program. And I don't like debating about words. This is not important. That's important thing is that we do the right thing, but the words should not prevent us from thinking in the right way. That is to say, if you assume the validity of the standard model, the only thing that you can do logically and statistically is to measure the free parameters of the standard model, because these are your only freedom to move in the space of hypotheses. And then the LHC has done already a lot in measuring the standard model parameters. For example, the Higgs mass has been measured, as Fabio already mentioned, to an accuracy which is better than what is needed for any concrete application, at least I'm aware of. And there are plans to improve the measurement measurements of the W boson mass and sin theta weak by factor of 2 by a very challenging and complicated experimental and theoretical combined work. But on the other hand, it is true that we want to do these things for sure, but the bulk of the activity that we want to carry on actually is testing the standard model. And in this, to do this, we necessarily have to compare the standard model with some of its extension. And the signal strengths or the kappas that these rescalings with respect to the standard model expectation are examples of standard model extensions, in the sense that in the standard model the kappas are equal to 1, so they cannot be measured within the standard model, but they can be measured if you think that there is an extension to the standard model with different kappas. We have plenty of examples in the times of the LEP E+ E- collider, the late 80s or 90s. People asked the same question and answered in terms of what are called the Electroweak precision test parameters that have been decided precisely to deform the standard model in a controlled way, which would have been effective. So the most effective and useful deformation of the standard model was encapsulated in the Electroweak precision test parameters. And here, just to remind us that, of course, testing standard model calculations is very interesting and it's useful as well, and it's necessary. For example, the first plot that Fabio shows, since we are essentially sure that in the vast majority of these many cross sections that have been measured, that there could not have been new physics. For example, I know the inclusive production of a Z was constrained so well by previous knowledge of the Z that we will not expect any new physics, and that provides indeed a validation and a confirmation, the test of our ability to do calculation, which is extremely important and useful, but of course is not the final goal. So we should actually think to this as a PSM precision program, which should be then designed having in mind what may waiting for us to be discovered. Okay, so what kind of real new physics could exist and be there in the future to be collected data that we will be able, and this is what Fabio already mentioned, that we may be able to discover only if you search for it in the proper way, only if we exploit correlations, only if we make a refined guess, okay, and correct guess of how this new physics will manifest in data. So only if we have a picture of at least the broad features of what it could be, then we have a chance to discover it, okay? Or at least we maximize our chances to discover it. So this program, very much like the LEP Electroweak precision test program, in its own, as we will discuss, a smaller domain and area of applicability, had to face the quest for being as agnostic as possible. So we would like to structure our exploration of the unknown in a way that relies as little as possible on, here I call them concrete, but I would say specific new physics models or set of models that we call scenarios. The reason being, any sensible person will tell you that most likely the right new physics model, okay, the one that really exists, has not yet been formulated. So it may very well be present in the data, but we may not find it if we just look at it guided from the things that we already have imagined. So the reality may be something we have not yet imagined. And so we have to make any effort to make this modeling, if you want, of the unknown, which means deforming the standard model in some particular way, in a way like Electroweak precision test physics, like LEP did, in a way which is as broad as possible, and as we say, as model independent as possible. This must not go into contradiction, okay, with the fact of learning as much as possible on the models and the scenarios that we have already thought about. For example, we may ask if the Higgs is composite, and we should be able to answer also using indirect searches, also using the LHC precision program. And either this fits in our generic, say, toolbox, in our generic box where you put new physics, or you have to make dedicated studies, right, to that particular possibility. Now, in this, so I will not speak much about this. So as Fabio already introduced, we see a very clear prime, or first at least, candidate BSM model, which is here in quotation mark, And this is the standard model EFT. Now, for the experts, this is going to be the so-called linear standard model EFT truncated at dimension 6, which means that I'm going to add to the standard model the operators of interaction of energy dimension equal to 6, of course, on top of the standard model ones, which are famously of dimension 4. This is a model only in quotation marks, in the sense that for practical purposes, it is really our model. So it's the Lagrangian we use to make predictions, and as a function of the three parameters of these models, which are what we call the Wilson coefficient, the coefficient of this new interaction operator, as a function of those, we build our likelihood, we make our predictions, and we compare with the data. On the other hand, you should not think to this as a beyond the standard model, say, first principle scenario. It's not like supersymmetry. It's not that we stop doing supersymmetry, now we do EFT. No, it's much more interesting than this. The EFT is a container that contains possible models, okay? That contains, and we would like to make sure of what kind of model it contains, and what kind of models it contains of those that we have hypothesized and of those that we have not, okay? Giving us the opportunity to discover also things that we have not thought about. But it's important when we listen and talks about standard model EFT to, especially this you can do, especially if you have a beyond the standard model expertise, to try to visualize concrete examples of new physics that could lie behind these interactions, which written in this way to many people do not mean much, but they do mean if you have the example and the guidance offered by DSM. Okay, so in this context, one can define, one can think to LHC physics built around, okay, this precision program. We will gonna build it around this EFT interaction Lagrangian of dimension 6. And so we will have to look at all its possible manifestation. And there are two classes of manifestation. In the context of LHC physics, we call low energy observables those whose typical energy scale is actually pretty high, is the Electroweak scale, say 100 GeV, and we call high energy, okay, all the cross-section measurements and all the other observables which have a characteristic scale much higher than this. E could be, for example, 1 TeV. It's kept variable here. In this slide, you see simply dimensional analysis at work. The fact that an interaction operator at dimension 6 has in front of it a coefficient which has the dimension of an energy to the -2, which you can write as 1 over lambda square. Now, this lambda, you can think to it as proportional, even if not equal, to the mass of the new particles that you are integrated out, of the new states that you are integrated out when you want to obtain your EFT. So it's the mass of new physics. And by dimensional analysis, the relative contribution this gives to an observable is of the order of the scale of the observables divided by lambda square. And so at low energy, by definition, you are measuring quantities at a fixed energy. For example, the properties of the Higgs boson that Fabio discussed a lot. They are already an established success of the LHC, which, however, have and will have to face, and will important, of course, to improve also in this direction, the challenge coming from systematic uncertainties. Because Fabio was speaking about 1% as target, and indeed, this is already a good target for final precision of the LHC. This should be compared, for example, with the precision of the LEP experiment, which was instead 1 per mil. Okay, so it is clear that the LHC has the precision potential, okay, but it's a precision that is less precise than the one of LEP. So this means, for example, that if you try to measure the properties of the Z boson at the LHC, you will not be competitive with what could be measured at that LEP about the Z boson, because the Z boson could measure at per mil, and we are at the same type of processes at the same scale. Right? We can learn a lot from the Higgs for the reason that the Higgs could not be produced at that LEP. We can learn a lot from the top, and for the reason that top could not be produced at that LEP. And so we have been already able to probe deformations of the standard model. So if you want operators in this Lagrangian, which give larger contribution to the Higgs and to the top than to the Z, for example, composite Higgs. These new probes using the Higgs have been particularly spectacular and extremely useful. But it should be kept in mind that we cannot say face directly, okay, the imagine directly to improve with respect to LEP if we don't have systematics of 1 per mil that we do not have. But we do have a lot of energy at the LHC in the sense that we can, for the first time, measure accurately again, accurately at this, say, not at the per mil level, but still measure accurately, observables at an higher energy scale where the manifestation of new physics becomes larger, and so they could just overcome systematic uncertainties. And furthermore, if you have systematics under control, then all what matters is the statistics. And so the luminosity, that is to say, what will improve, will increase during the high luminosity LHC phase in the next 20 years will be easily, if you want, exploitable to make progress, because you will not have this showstopper of systematic uncertainties. And this is somehow a combined exploration that exploits both the energy frontier mechanism by which the LHC functions, so produces high energy reaction in the way that allows us, for example, to produce new particle, but it also allows us to measure observables at high energy, and there may be something to gain in this intermediate direction. Okay, so these are what we call high energy probes, and if you want to define them quantitatively in an ambitious way, we can do as follows. We can take again this LEP experiment, which was measuring a lot of electroweak properties, like I mentioned before, at an energy that was 100 GeV, because that was the energy of the experiment, at an accuracy of 1 per mil. So suppose you have an effect, so a new physics operator with the lambda such that it gives precisely 1 per mil correction to your observable at LEP. Well, this was, let's say, just at the boundary of not being seen, because 1 per mil was the uncertainty. This same effect gets amplified by 2 orders of magnitude if you measure instead the same observable, or if you measure the same the effect of the same operator at the 1 TeV energy, becomes 10%. So the moment in which you can measure at better than 10% at an energy which is 1 TeV or larger, then the hadron colliders win. Okay. So the other colliders win even in processes, or if you want, in deformations of the standard model, in physics operators that have been very well measured by LEP. And this is just a very small fraction of all things that can happen inside this D equals 6 Lagrangian. So we like to say that the precision program of the LHC is a continuation of the LEP precision program, because we know the enormous impact of LEP in all textbooks, you know, about having confirmed the description of weak interaction in terms of gauge theories being the result of LEP, right? So we all would like to go in the same track, but actually this comparison is not fair toward the LHC, because the variety of processes that you have access to, okay, is so much superior to the one of LEP. And so the number of processes on which LEP, if you want, didn't have per mil, but had 0% accuracy, is so large that comparing the two is actually a little bit unfair. The LHC will allow, of course, many years later, but will allow a much more complete, okay, exploration, and also a much more challenging one, because if I look at the papers from LEP, the 80s, well, at this point now they have a few tens of numbers. I mean, now I'm exaggerating, but in comparison with all the observables that we can assign at the LHC and all the effort that we have to do to make the prediction, I think it's simply not comparable. But also the outcome, as I was saying, could be way superior in several senses and directions. Okay, so this simple table was just to show you in concrete that this 1 TeV 10% was already achieved several years ago when the LHC was still running at 8 TeV. This process is neutral Drellian, is the production of 2 leptons, one of charge plus and the other of charge minus at the 8 TeV LHC. And at the bottom of this table, you see the highest must be in the one around 1 TeV, indeed, that where you see the breakdown of uncertainties is dominated by the statistics. So by the fact that when you increase linearly, in particular from 8 TeV to 13 TeV, the center of mass energy of a hadron collider, the cross-section in the high mass bin does not increase linearly, increase exponentially. I can already tell you from this slide that I expect that the statistical uncertainty will go to 0, the systematic uncertainty, and in this case also the theoretical uncertainties are under control at the level, let's say, of 2 or 3%, and this allows me to tell you that the run-2 will, or actually has already, even if we don't yet have the result of the analysis, so the collected data will already be sufficient to surpass LEP. And this plot is aimed to show exactly that. You have 2 effective field theory operator of energy dimension 6. They are parameterized in terms of this dimensionless coefficient, which are the 2 two of the four oblique universal parameters that were used in lab times, and this is the lab contour using the old data, ATV, but just look at the projection, which will come from the data that we already have, 13 TV, 100 inverse, so 100 inverse femtobar, and then how it improves, of course, with the luminosity. And remember that you have to combine the green vertical band with this potato shape, and you see that you already, with current data, you expect to have, if you don't see new physics with respect to the standard model, a little spot in this big, outdated old ellipse, which was the lab results in these new scales. Okay. So, generically, what is that we need in order to make a useful or successful high-energy probe? Well, we need accurate experimental measurements, of course, and you may say, I'm a theorist, well, then let's let them do. Well, not really, because you must make these measurements in the right kinematical ranges. Now I'm speaking specifically about high-energy probes, but all this, I think most of it just applies the same way to all type of precision that you can do at the NDC. So you have to optimize your analysis, and in some cases inventing also the new and the right observables that are needed in order to have sensitivity to the effect that you want to see, right? This is the BSN guidance. You will decide that you want to see, you want to study the standard model EFT, then you will have your standard model EFT operator, and you can characterize the type of observation that you have to make. Of course, this requires dedicated experimental analysis. All this cannot be a spin-off of some other analysis trying to measure generically something related with, I don't know, dielectron or boson production for careful job of systematic reduction, but also from the experimental side, I can see quite a number of aspects which would be game changer if it was possible to break certain barriers in what they are able or not able to do. For example, precision with boosted hadronic objects is not yet, at least not many, I think not many people tried. We need accurate theoretical predictions, and again, these have to be made once again in the right kinematical ranges and of the right observables. If you want to, so in order to be useful to the general endeavor. In this context, for example, the high-energy probe makes particularly relevant Electroweak logs enhanced in the infrared, which enhance Electroweak loop correction. There has been even a proposal in this paper concerning PDF uncertainties for a program of fitting the Parton distribution functions, these unknown that we have, these inputs that Fabio was mentioning about, together with the EFT parameters, in order to be completely sure that we can exploit at best the data that we have in order to constrain the PDF without at the same time fitting the new physics effect away. And this is particularly important for the high-energy probes because at what we say large X, at large energy, the PDF uncertainties can start becoming larger, and they are subject to uncertainties of different type. So it is somewhat specific of the energy probe, even if, of course, PDF are important also for Higgs couplings and all the other low energy probes. And of course, also the new physics prediction have to be made accurate enough. So you have to be able to tell what is the expectation that you will have within the effective field theory. And well, technologically, it's very important that they are made in a fast way because the goal here is to explore so many directions, so many theoretical possibilities encapsulated in all these effective field theory operators that if you really want to do this, then you cannot really do by individual Monte Carlo simulation for each point in the physics space, because you will have infinitely dimensional, largely dimensional infinite grids that you will not be able to deal with. And last, but actually first, is the target, okay? So very much like beyond the standard model phenomenologist gave the vital contribution to things like searches for supersymmetry or many other exotic stuff, top partners, whatever you like. Here it is exactly the same game, the game that you are good in playing and that leads to result. In this particular case, again, I'm sticking to the energy probes, but similar consideration extend to many other things. You have to pair up operators, okay, and final states. So you want that the operators induces a growing with energy target in a final state, which can be accurately measured and accurately theoretically predicted as well. You have to characterize the effects that you expect from this operator, and so go back and design the type of measurements, and so the analysis that at the very end you would like the experimentalists to do in order to probe that direction. And in some cases, even define the observables. Now, the case of Drell-Yan is relatively straightforward, but just the moment you extend it, you go from the simplest Electroweak process to the next to simplest, you will see that this problem is concrete and needs to be addressed. You finally have and can assess what we say implications. Now, Fabio didn't have time to show one of the famous projections or tables that we have with the reach on the Wilson coefficients, which are the coefficients of these operators. Okay, they may seem quite boring, but as I was saying, if your eye knows what can hide behind these effective field theory operators, then it's much more interesting. That's why one important thing is to make sure that to make sure that all what you want to probe is probed by this analysis, and also to translate on concrete models the sensitivity that comes maybe from this rich table. On top, of course, of comparing all this with the rest of the universe, which are constraints that come from flavor, that come from all the other sources, all the other sources of information that there is in the universe. I just want to spend one more slide on this Drellian, because it's such a simple process where all these things that we are talking about, I would say, exist. So we have predictions which are accurate in the standard model, in BSM, and so you can, for example, quantify the impact of PDF uncertainties and see that is the dominant one. The result here is the combination of the previous ones. It's compatible with the other ones. Left will be this big contour that I have not shown here anymore. For example, you can notice how much lower is the sensitivity floor. Okay, so lower than what we can estimate as rich today, based on baseline PDF uncertainties that we have with current PDF sets, and assuming systematic uncertainties at the level that we find reasonable, and see how much below, okay, the floor is, how much space there is, at least in line of principle for improvement. You have to explore the likelihood as a function of many Wilson coefficients, because again, the purpose is to try to explore as much as possible, and for this you have to provide fast predictions. In this case, are provided by event reweighting. And then you can pick up one model, and for this simplest, study, we picked the simplest model, okay, the Z prime, everybody's model, the standard target for the beginning that was super studied at the beginning of the LHC. And I would say that this plot looks quite different. This projection plot concerning what the luminosity LHC could do, I think it looks quite different from what so at the beginning of the LHC people could have envisaged. This green contour is the projections for the High-Luminosity LHC direct searches for the resonance, and all this region here in the plane of the mass and the coupling of this resonance for different directions in the way in the current through which this Z prime is coupled, you see how much space there is, which can be covered only by, say, high energy probes, by EFT studies, by precision studies, and that cannot be covered directly. And you also see that there is space for 5 sigma discovery, okay, which is given by this line here. And given the possibility, as we say, of characterizing the properties of this Z prime if you discover it. Now, here, one discussion that one typically has is whether a 5 sigma discovery of an indirect effect could be seen as a discovery or not. Well, in some sense, yes, in the sense that neutral current have been are called in books a discovery, and well, observing this effect would be a discovery of a neutral current, literally. So but it's true, of course, that well, no, and this somehow shows that you can learn about what type of new physics there is if you make some work. Okay. Right. So the next topic is, I mean, in some sense, the Drellian is good because it illustrates the things that you will be able to do in a very simple situation. But of course, it's just the simplest Electroweak process. And the next to simplest is the production of 2 bosons rather than of 2 leptons, 2 Electroweak bosons. And here it's an incomplete list that is cut by the fact that the slide finishes on some experimental results and many papers that have been done in the context of this process, and many more will be needed. The type of new physics that you can see in the production of 2 bosons at high energy could be affecting or modifying the scattering amplitude with helicity 0, the longitudinal so-called amplitudes. And this kind of effects, you would like to probe them, if ideally, looking in a correlated and combined way with several processes, like, for example, like WZ, 2 really vector bosons, WZ or WW, or a vector bosons like a W or a Z and an Higgs boson, because by the equivalence theorem, you know, longitudinally polarized Ws go together with the Higgs, and so the effects are correlated. What has been studied? Well, there are experimental papers, also very recent ones, some of which I mentioned. In terms of projections for the high-luminosity LHC, well, we studied fully leptonic WZ, and other people did. Some other people studied ZH, again, 2 leptons. And I would say, I mean, I'm happy to be contradicted, more or less that's it. So this gives you the variety, a flavor of the variety of things that one could do. Just trying to make the Z decay into hadrons, for example, would require a dedicated different study, or WW versus the ones that we have been studied, WH. So even here, there is a huge variety of things that have not been attempted, while the potential is already demonstrated by studying this simple case, which, however, is plagued by a small branching ratio, because it's rare to have WZ going fully leptonic, which gives this little vertical band, okay, on a plane that I'm not going to explain, but it corresponds to 2 parameters that people experts in lab physics recognize as one of the parameters that were introduced to describe the linear gauge coupling. And this other plane is for the expert of composite Higgs, where they can say in coefficient of operators that are typical of composite Higgs, what is the impact of this kind of probes. But here, the gain, for example, with the hadronic decaying object, if the experimentalists could deal with that and do precision, could be enormous. An item that I decided to touch briefly about, even if it's somewhat technical, has to do with the issue of the so-called EFT validity issue. And the reason why I want to touch this topic is because it illustrates what it means really studying EFT with a beyond the standard model perspective in the following sense. So when we see some EFT result, or we make some projection, we have to have in mind again that the effective field theory is a container of models. It's a container of models and of scenarios. So the first question that should come to your mind is, which class of scenarios and of models are we probing? Okay, what are the implications of what we extract from the EFT? Like this very simple example of the Z prime was telling you what are the implications for that probes in Drellian. Now, in this particular case of IRG probes, one question that comes related with this is the following. We know that effective field theories have a finite upper cutoff energy of validity. So they describe the underlying UV physics. Okay, so they are valid description of the underlying UV physics. Okay, so they serve their purpose of container of UV model only under certain condition, in particular only on if you probe observables which do not have too high energy. Otherwise, you will hit the cutoff. Okay, and so the description that you were thinking was describing the UV is actually not working anymore. So you want to assess to what extent this is the case, to what extent the limit, or even more importantly, the discovery maybe that you have established based on this EFT approach, does it comply or not with the actual prediction that are expected in the UV, and in which cases it does, and in which cases it does not. So, and as I was saying, the key here is the energy that you have been probing with your experimental analysis. Okay, so the first thing that you have to do in order to answer this question is to look at the sensitivity. This is the Wilson coefficient bound, let's say, projected, of course, as a function of the maximal mass of the WZ system. It doesn't matter. It's the maximal mass of the is the maximum of the typical energy of the data that are used to make the analysis. So the sensitivity, a priori, if you don't cut it, relies on predictions made in the EFT and compared with the data in the entire range, okay, which is accessible by the LHC. This curve is constructed by removing, okay, the data that come from too low energy. For example, this one corresponds to 3 TeV. So I don't put data below 3 TeV, and I see that the limit does not change, which means that the limit was not affected by the region 3 to 5 TeV. It's somewhat affected by the region from 2 to 3, because this goes a little bit up. Of course, the limit gets worse if I remove data, and so on and so forth. Okay, so what does it mean? It means that, for example, if I have a cutoff, that is to say, if I have a UV theory which does display new particle with a physical mass, and that is what is the cutoff is at a scale of, for example, 3 TeV, then, well, it doesn't matter, because if I look at data at 2 TeV, I still may well model them more or less fine with the EFT, and so my limit would apply, would be self-consistent inside this description. But of course, if my cutoff is 500 GeV, then, well, probably I should not use the EFT, but go and look for the particle directly. And on the same plot, here I have another, these theoretical prediction lines, if you want, that correspond to the relation that there is between the cutoff of the effective field theory, that is the mass of the new scale, so the things that I have to monitor here, okay, to make sure that one does not exceed the other, and the prediction that it makes for the Wilson coefficient. For example, this line here corresponds to a scenario of new physics in which the quarks are strongly coupled, so they have coupling 4 pi, with some new physics at the mass m. The Higgs is also strongly coupled, 4 pi, and so you integrate out new physics, you get 16 pi square over m square, which mediates then this operator you see is QQ bar Higgs, and so by the equivalence theorem, this Higgs becomes longitudinal, and becomes one of the operators I'm studying in this diboson search. So this line is fully strong, and what is here in this gray area is just excluded. So here there cannot be any theories, and the reason being that no coupling can exceed 4 pi, or if you want to view it more mathematically, from the viewpoint of the perturbative unitarity argument. So this is the first sanity check you can do. If your bound sits here, so if this line had to sit here, then this analysis would be useless, because it cannot apply to any sensible theory at all. Okay. Then there is another line which corresponds to a different hypothesis on the structure of the underlying UV theory. Maybe the couplings is plausible that actually they couple dominantly through gauge interaction. So this coupling is GW. Then there is this is the W boson, the real W boson, which then will talk with some other heavy sector, which is not drawn here with mass m. But the W boson will also be strongly coupled. This is models on which you have a strongly coupled composite W boson, which may perhaps exist. And in this case, they will give this other line, okay, 4 pi GW, which is smaller than 4 pi. That's why this line is lower, okay, and this is a strong Trina gauge coupling. And finally, the class of theories that we, for some reason, for some theoretical prejudice, we are more interested in are those in which the quarks and also the gauge are weakly coupled, in which case you have GW here and GW there, and so the line is even lower. So now you see that the LAC and the high-luminosity LAC in logarithmic scale, of course, are far from this line, okay? Are far below. So you can really say that these constraints do really apply to an underlying theory of the weak type, like, for example, to composite Higgs. This was not the case at using the ATV LAC data, and this gave to some controversy, because people were saying, okay, you see, I'm better rich than LEP. This is LEP on the ratio of the same operators. I have better rich than LEP. I'm lower. That's true, but you're getting this rich in a way that excludes, okay, you applying, if you want, this to this type of scenarios. Then you have to try to interpret the search in this type of scenario. You will discover that in this type of scenario, the search will not be effective at all. The reason being that this sensitivity exploits a growth with the energy which is too much with respect to what is predicted by these weak scenarios. By now we can, provided, as you see here, we rely on accurate measurements. So if instead of an accurate measurement, we just make, we are not able, for example, to make prediction that we say characterize here with the idea of having 100% systematic uncertainties, then you go back hitting the weak line. Okay, I am over time almost. So let me just mention that in the same diboson process, there are operators of different type that produce corrections to the amplitude with transverse polarization. And here there is different type of challenges and stuff to think about. One being the fact that you will hide the new physics because of a mismatch in the helicity amplitude that corresponds to the standard model dominant part and the new physics dominant part. They don't match. So if you measure circular polarization, you will cancel the interference, or if you will not measure polarization. But if you measure plane polarization, and I'm speaking about the polarizations of the emitted W bosons, you can make it. So you will need to include in your set of observables also things like the azimuthal decay angle of the vector bosons. And this, of course, is a complication because normally you have the production of two bosons that you characterize in terms of the variables of these two bosons. That's not enough if you want to have sensitivity. And this is it's already been taken by CMS in this channel, showing how much you do gain. And then this suggested this type of consideration suggests to us and to many people that are working on this type of activity that actually, if you really want to make the best use of the LHC result in order to exploit all these angles, for example, and this is just as again the next to simplest Electroweak process, which still has two particles decaying into four, so a lot of angles and variables. If you really want to exploit the best, you may need novel machine learning techniques that are being developed and also being contributed. In particular, in this plot, you see that there is almost a factor of 2 to be gained in sensitivity with respect to what is called here a binary analysis. That would be an analysis in which you measure certain observables optimized to the reach of the EFT. In particular, you do measure this azimuthal angle, which is so important. Still, we are not being able, at least, to design a binary analysis which is as good as what you could in principle get with one of these, say, unbinned. These are similar to the matrix element method techniques, which, however, are based on model machine learning techniques, which are being developed precisely to study this type of problems at the LHC. Okay, so let me conclude that I agree with Fabio that there is great physics ahead of us, and that 20 years may be just enough time to get ready to really get the data, which we will keep getting in the course of these 20 years, but we will not get fully until the end, right? But in the meantime, there is many things to do, which need a dedicated work, and so especially synergetic work between experimentalists and people doing predictions, PDF feeds, and of course, the standard model guidance in the form that I tried to describe. I consider this EFT a useful models container, okay, inside which there are models waiting to be discovered. Well, I don't need to stress again that all this is very much work in progress. And if I just want to mention one thing, even the very classification, since I spoke quite a bit about this high energy probe, even the very list of all possible growing with energy effects that have a chance to be seen at the LHC, a complete list, as far as I know, does not exist. A voluntarily incomplete list, which aims at substituting, but there's not the purpose, high energy probes, Higgs coupling measurements with the energy probes can be found in this paper that gives you a flavor of how many opportunities and possibilities they are. And I also briefly mentioned the possibility that, so for sure, we will need experimental analysis that are dedicated to the EFT, that make measurements in terms of unfolded cross-section measurements that are designed and optimized for what we want to see in the EFT, that's for sure. But maybe one can also make a step forward, in some case, a further step in super optimization for the EFT signal, which may require a new statistical tool, making, so being able, imagining that us and experimentalists are able to cross a number of barriers associated with all this difficulty, designing using neural network, like I was discussing before. I think that is simply great. Thank you.
Thank you, Andrea. Now we can open the discussion. The idea was to leave the stage to the 4 panelists that we contacted early on. So Michelangelo, Adam Selli, and Christophe. Let me see if I... So please, Michelangelo.
So maybe I leave here this slide that we prepared with Fabio, our questions to the audience. Okay. And I leave to Michelangelo if he wants to take from that or not. Okay, Fabio?
Thank you, Andrea. Thank you, Fabio. I go first because I have a terrible internet connection and I may just drop out any moment. I have basically 2 questions. One is, Andrea, you showed, of course, this interplay at high energy of, say, Drellian observables or diboson observables with electroweak precision tests. But there is no indication there in those comparisons of the relative sensitivity between these high energy observables and direct Higgs properties, say branching ratios, for instance, etc. So I was wondering whether there is already a picture of, as we go to high luminosity LHC, the direct observation of Higgs properties, which means mostly, say, branching ratios or even better ratios of branching ratios across different decay modes, compete with those.
I think not.
And the other point let me just state the other one, please. So that then I'm done. And the other one goes to the issue of the PDF uncertainties. And I was wondering to which extent use has been made so far of, say, ratios as opposed to absolute distributions. For example, when you look at die bosons, of course, you are after, say, longitudinal scattering, and the absolute rate of LL final states will depend on the PDFs and therefore has the systematics. But if you look at the fraction of LL over TT, say, in that, I would assume that the PDF uncertainty goes away and you really have a more direct probe and a much more robust, somehow, comparison against the possible.
Okay. Michelangelo, are you there?
No.
Your voice dropped for a second, for more than a second.
It was just like, you know.
I think he dropped, so.
The right moment. You know.
So you say, okay, so I think, so concerning the impact of Higgs couplings on the interplay of Higgs couplings with respect to the plots that I've shown specifically in this talk, no, this interplay, I mean, in this direction. So remember that many of these plots, for example, the WY plot is made on a plane, right? So it's not the result of a global analysis. But in many of these plots, I would say that Higgs properties, I think, are not relevant, with the exception probably H gamma. This I will have to check. But if you really want the answer to this question full-fledged, then this is the paper by Francesco, right? In which, as you see here, so you can. So the question they asked is very similar. So how you could, if you want, replace the Higgs coupling? So you would go and look at each things that you learn from the Higgs coupling, and now this could be learned from one of these high energy probes. So I would say that, you know, the inverse of your question is answered in that paper. And there are things like multi-bosons, may be difficult to see. Concerning instead the fact of fitting ratios, I perfectly agree. And actually, even in the simplest case of Drell-Yan, the fact of being differential, so which is the same as taking ratio, right? If you do the fit including more things, then you are sensitive also. So if you have two beams, then you're sensitive, and you have a very powerful knowledge of the ratio of the two beams. So this is inside your fit, and so this is one of the things that we actually noticed in Drell-Yan, and you can also see here by the fact that the combination is narrower than the overlap, and this you can understand by the fact that there are certain directions where the PDF uncertainties indeed cancel when, but only when you include differential measurements. In this case, I think it was, it was I think it was the up PDF that was dominating in both cases. Now I should recall it better, but yes, I think, however, that you will agree that yes, one can think in a very dedicated way, but one can also, so the more you go differential, the more you will address this type of questions.
Yeah, I agree, of course. I mean, there is a slide. I mean, there are a few plots that were done by the EPFL collaborators. I don't know if I can show them, but they make it visual, the answer to the question of Michelangelo. But I can show them later if you want.
Christophe?
Yeah, so maybe I can start with, two questions. Maybe one general about EFT. So you discuss, this, let's say this fit, and you report the fit, as bound, let's say, on the Wilson coefficient. But usually what is often missing is actually the correlation matrix, that exists in this fit. And which, first of all, how can we report this, this correlation? And second point, how can we actually interpret those correlations, and how can we use them maybe to learn also from BSM model? You know very well that in some large class of model, you actually expect to see huge correlation among those operators, right? And so
yeah,
we can certainly learn a lot from those correlations. So it will be good also to find a way really to report and exploit them.
Well, I think from the purely BSM viewpoint, once you will have this likelihood, including not only the measurement, but also the correlations, then in order to, then you will really have to compare this with the model, or at least with the scenario. So if there is a correlation, you have to. So this, of course, it's obvious, right? That there must be a way to access the likelihood and not only the measurements, for the precise reason that you said. Right? Maybe Fabio wants to add something.
No, exactly. Yeah, we show currently in the fits we have these huge matrices where we show the correlation of the uncertainties, right? Typically in the correlation operators. fit collaborators visualize as these beautiful plots that which I can show if you want after. So visualization is complicated, let's say, because it's always so simplified in nature. But I guess, yeah, the likelihood at the end will be the true content of the output of the fit, right? The fact that you have a whole distribution of probabilities, so on.
Of course, realizing the likelihood is something that will be difficult also from the experimental side, right? So we need to find a compromise there. So I don't know. Yeah. I see that Sally has also her hand up. Otherwise, I can continue with the second question also.
Well, actually, my question is kind of a continuation of yours, Christophe. And that's, how do you estimate the uncertainties on these fits? Because you're making all these assumptions about 1 over lambda squared, 1 over lambda the fourth, higher order corrections in QCD are included, not Electroweak corrections. So to go along with these correlations, you need, I think, a more rigorous way to understand whether these things are good theoretically to factors of 10%, 20%. How do we go about, what do I even calculate to figure out how to do this?
Yeah, so this is somewhat, to some extent, an open problem, okay, I think, in the sense that, as you know, conceptually, these kind of fits NLHC are very similar to those that are made by the PDF collaboration, right?
Exactly.
They are like somewhat fitting the infrared, we are fitting the ultraviolet, but somewhat in the end, they really encounter the same kind of problems. And when you talk to them, who are the experts of this, and done this for many years, you realize that there are some things that have never been done. One of them, well, they're starting now. I'm simplifying a bit, but so one of them is exactly what you're saying: the missing higher order uncertainties, what we theorists normally call theoretical uncertainties, at least the purely perturbative ones. So what these have not been included for so far. Now they are, they're started, and the way they do it, they include it in the covariance matrix as an extra term. There is a technology that they have tested and developed, on which they, some of them at least, they rely upon, and that could be, in principle, my understanding, extended to our case. I remind you that in all the proto global fit that we are doing now, which need to be considered as first steps into a new business, right? So we are still understanding.
I agree with that.
The theory uncertainties are not there. So, I mean, we have not included, for example, the reduction uncertainties coming from a better knowledge of the coefficient function and extra leading order, right? We use the change in accuracy, we use the change in central value, but we don't include the improvement in precision yet, right? And so some others are done in leading order, right? So, I mean, for the moment, we do what we can and we explore somewhat all the directions that we think are important to know. But I think what you are rightly so thinking about is to have some kind of agreement on methodology, on the way that you know, the uncertainties are listed, are considered, and then one day maybe even combined, right, in the idea of what they do in experimental analysis. And certainly the missing higher orders are one of them. The experimental uncertainties are another huge problem, right, for us, because again, the way that we use the data right now, for example, some analyses have produced many distributions, but we can only use one distribution at a time from that analysis right now.
Why is that?
Because the correlation are given beam by beam in that distribution, the correlation matrix, but there is no correlation matrix of different distributions, right? So as long as you, I mean, first of all, you have to choose distributions which are not very much correlated. And then you can still use, but there are some correlations which are inevitable. So, I mean, we are really moving the first steps, right? I mean, there is so much to do even at that level. And so, certainly true, what you're saying, a lot to do, I guess, a lot to do to get to a point where we will somewhat trust and a robust list of uncertainties. I think we are still in the phase where we are checking our sensitivity, really, in practice. Multi-dimensional, but somewhat is we are testing our abilities to understand where the information might come from, or which one is missing. This is, I think, is the level right now that in practice we have.
I see Adam with the raised hand.
So I have maybe one comment. So Andrea was stressing quite rightly so the importance of high energy measurement. Yeah, but maybe I would comment that one should not forget about the low energy measurement too, yeah, because there is a lot of interesting things happening there too. Yeah, so there are low energy measurements where you can also compete with lab. The prime example, of course, is the W boson mass. So this one everybody knows, but maybe one less known example is that for the measurement of the W boson couplings to leptons, LHC is now better than LEP2, and it actually contributed to elucidating some anomalies that appeared in LEP2 after taking into account the data from the LHC. This LEP anomalies, this lepton flavor universality violation that LEP2 seemed to hint at is gone. Yeah, so there are also places to compete. Yeah, so that may be a comment for that. And I would maybe ask a provocative question. Yeah, so it seems that so this program of precision is going like a big train in one direction for many years already, but now it seems that maybe the real action is happening elsewhere, yeah, in flavor physics, and that may be where the discoveries and the Nobel Prizes are. So do you think that would it make sense to make a big U-turn in this precision program and commit much more resources to trying to address the flavor physics observables like RK, BS2 was already of course done, yeah, but like RK star, maybe some other observables. Would it be interesting for the LHC precision program?
So the provocative answer is that there are thousands of people doing a great job in flavor physics, and that's why they get anomalies.
Yeah, but it's saying
No. So, and then instead so the first thing that you said, it's of course, it's very interesting. But also the second one, you know that high energy probes have been, people, David, for example, have been studied also in connection with possible explanation for flavor anomalies. So one of the questions that we had is, so there is flavor physics even outside the meson decays, right? Mm-hmm. So, and then this operatively means how do we incorporate in the effective field theory flavor knowledge? Now, flavor knowledge could be flavor bounds, because there are a lot of flavor bounds, flavor change neutral current in the quark sector, but also the flavor anomalies now. So one thing that would be worth discussing is how to make a flavor pattern that complies with the possible anomalies and that can be used to guide. And we know already that there are examples of high energy or medium energy, because at this point even 100 GeV is high energy with respect to flavor that can contribute to that. Yes.
Yeah, let me add one thing that I'm not sure you were somewhat alluding to, but I mean the other half of the answer is that there is power, like in the IPT NHC, right? I mean, for people doing IPT, there is a power to make an impact in flavor physics observables, right? I mean, I'm not going to tell David and having today. I mean, there are many suggestions, right, that go through some kind of UV completion, right, that works, or maybe even less interesting as deep, right? But you know, with processes like Gradian, taus, or differences, there we know that there is a clear clear power to do something in the tail, right? To check the tails, whether there is flavor violation in the tails there, and the obvious sort of things which are not obvious anymore, because now you have some constraints coming from all energy. So there is a complementarity between, in general, between flavor physics and IPT, and I think now is even more manifest. I mean, somewhat, it's true that some kind of these models have been studied in a resonant way, right, in a complete way at LHC. But there could be also a region for some, depending on the mass, that we actually access to those models in the EFT language.
Okay. So to let me understand you, so your opinion is that Atlas and CMS should rather take advantage of the complementarity of high PT rather than trying to compete with LHCb and Bell to make the discoveries. Yeah,
I think we should do everything.
Oh, well, there are thousands of people. I mean, there are thousands of thousands. I think what you're saying here is that there is a number of clear opportunities that are not explored, and that, by the way, overlap, as I was saying, with flavor anomalies, clearly, and that's already demonstrated. And so we don't know what else to say. There is a need of working in order to assess the potential of those opportunities. And if there is an anomaly in flavor saying that there is new physics in the Electroweak sector, then I don't think I have to look just exactly on the same analysis that will give the hypothetical Nobel Prize for flavor, but I should actually look more broadly if I want to make a useful job.
Yeah, another example that you were telling me, Andrea, right, in this mu tau, right? I mean, the mu tau.
Yeah. That's what I say. There is a clear thematic overlap in this really same thing. But then there is also the essence is that also flavor is so it's a big industry, right? It's a little things that people working and understanding things, and here I think we are less advanced, especially as far as it goes with because with Higgs there have been a lot already. There is a community that is. So with enlarging to the EFT IPT, there are, as Fabio discussed and I discussed as well, things that to be understood and that can be clearly complementary with flavor and help directly also maybe with flavor analysis.
Okay, thanks.
Are there any questions from the audience? I think we are late, so maybe. Okay. I see a raised hand from Tanya. Can you unmute yourself, please?
Yeah, I'm muted. I cannot put on the camera because of bandwidth and so on. So you had this question slide. Can you put it up again?
Yes, I will. Please go ahead with the question if you.
Yeah, but I wanted to refer to something on the question slide.
Yes, I imagine.
Yeah.
I go as fast as I can.
Go as fast as you can. Exactly. Very good.
Here we go. No, thank you.
Yeah.
Here it is.
Yes, and a bit more down if possible. Yeah. So what do you mean with the last point?
The last point.
Yes.
Yeah.
What do you mean with integration, and what do you mean with how to?
So maybe Fabio wants to. So we really think that there is too much distance between well, even between the different communities of theorists actually, but for sure there is too much distance with the experimental collaboration, and also the way in which they are organized maybe at the moment is not optimal to take up the challenges that we have. We will need maybe something more cross physics, like Higgs is not different from Electroweak, and TOPS as well, and maybe more topically devoted to the target in terms of EFT, for example. I don't know if Fabio wants to add more to this, maybe.
But I mean, I made an example. You already said it. I mean, there are all the ways of collaboration between theorists and experimentalists that I feel, I'm not the only one, of course. I mean, we feel that are not suitable anymore to face this challenge. We are making that there is progress, there are working groups and so on, but there are also structural. I mean, Andrea, maybe you can share one slide. I can show you. I give you an example, right?
Please, just go ahead.
If you know, you see how a normal is done and then it's seen, right, in the collaboration. I mean, you have an analysis on GGAs in each group, right, and each one goes on and does all the workflow of analysis and then gets the result. The results might be different, might be an unfolded one, might be a result which doesn't need to be unfolded, can be any kind of result. But there's a flow, right, where each group optimizes the observable that they want to measure to get the best measurement possible out of it, which is obviously a legitimate thing to do. But then the problem is that if you follow this path, then this result typically is hard to combine with anything else. Because to combine, you have to know huge table, right, of uncertainties and be treated the same way. You have to use the same RICO algorithm and so on. So when I show this to an experiment, we say, well, it's not true, right? And we work this way. I mean, we already go this way. So I mean, data acquisition is the same for everybody. Calibration is the same for everybody. Reconstruction object for most of the normal high-PT analysis is the same. Then from there on, it changes. So the selection, the mid-ranking working point on the log curve, all the details of the analysis that are proper to each final state kick in. Systematics evaluation is different, the type of analysis and so on. So from there on, if you have in mind that one day you have to combine a WW coupling Higgs to the one of the top or GG Higgs here, which they have done already, of course, right? The experimenters have done it with the kappa. But if you want to do it in a more sophisticated, I mean, more reliable way and provable way, then this is a huge machinery, right?
But I mean, yeah, okay.
Then you should use this, I mean, kind of a GPU-like way of processing information that you go in parallel. And then this could be easy to combine, much easier to combine, at the price of losing a bit of edge in the best of possible measurement, right? So yeah, it's a trade-off. And in this flow, the theorists, I think, would have a very important role, as everybody else in this game, to actually, help designing the observables, as Andrea was saying, which maximize the sensitivity, which are not the standard model observable necessarily, and so on. So it's an interaction that still has to be put there, created.
But I mean, these are different topics, right? One is a cross-analysis, inner experimental connection, which you're showing here, basically. And the other thing is, can I, as a theorist, jump into an experimental analysis at some point and give my feedback? So these are different topics. I don't know. I mean, my impression is from this slide you showed that it's even more separate, that every analysis is really different, even not within the groups, but every person, every analysis group does it differently for the one specific analysis. Yeah. So this is something which, okay, I'm not deciding this. I just wanted to know what you mean, whether you mean inner experimental discussion like you just showed, or whether you mean there should be more interaction between theory and experiment, and so on. I mean, there are all these working groups, as you said already, and my impression is that at least for the ones I listened to, there is a lot of discussion between theory and experiment, for example, and input. Yeah.
But I mean, the various things don't exclude each other. What I was, I mean, what we were charged to think for this presentation was more what, what could happen on the long term, like how, I mean, in 10 years or 20 years, not like today. There are maybe things that we could do, but to do them, we have to start now. And this will be the logic. And one of them could be the organization, the way that people in general, the community thinks about what is the best value of a measurement. Is in the fact that it's squeezed to the maximum sensitivity and you have a best measurement of something, or is the fact that you can combine it, right? I mean, these things are in competition. There might be a best optimized. Okay. Something also to keep in mind.
Okay, thanks.
Okay, it seems that there are no other questions from the audience, so I think it's time to thank the speakers and everybody who attended the seminar. And I think we reconvene with this seminar series in the next week. Grazie.
Goodbye.
Grazie, thank you everybody.